we were trying to finish the outline of the proof sketch. So if you look at your notes, you will see that we considered, we had these projectors. So I'm not going to write them again, okay? They're in your notes, but I'll just ask you to recall. So we had written these things. Okay, so this is just the very last part of the tech overview. I'll quickly finish it. Continued. Okay, so we had so you remember we had considered the this game with the different challenge modes, right? Independent challenge mode. You were there in the last class, right?
Yeah.
You were not there? You didn't watch the lecture? Okay, good luck. So yeah, so we'd considered this game, right? So the challenger is going to sample this state. I'm not going to write all the details, okay, because we already have it. Samples this, sends the state ASS prime, and evaluation at HSS prime to little a. Little a gets access to an oracle in which SS prime has been replaced with perp. Okay, and sends a bipartite state BC. Okay, and so outputs B sub B, this outputs B sub C. Okay, and you win if B equals B sub B equals B sub C. And you're given oracle access, so you get the description of A. Both parties get the description of A. Description of A being the subspace. Okay, so it's this subspace here, and in one case they get HB sub B. So let's call these primes actually. Okay, so so in one case they get access to these oracles, okay, H, B sub B. So B sub B is a bit, H is an oracle, right, and H0 and H1 were defined. Okay, I mean, if you don't remember this, it's fine. Let me not backtrack entirely. But so H0 is the original random oracle. H1 is H outside SS prime, and it XORs at SS prime. Okay, and so you get access to one of them, right? So B gets access to either this oracle or that oracle, either H0 or H1, and C similarly gets access to either H0 or H1. Okay, and their goal is to output which oracle they were given, right? So that's the objective. Okay, so this was roughly the game that we were looking at, and then we talked about okay, and then we were talking about the state sigma sub BC, right? And this is the quantum state that is output over here. Okay, so this is the sigma BC, the state that they get. Right, yeah, sorry. Well, you can come forward actually, there's so much space. Because yeah, I'll try to keep it in mind next time, but I don't want to erase and write again. So okay, and then this is sigma BC. This is the state that Bob and Charlie share before the before they perform the operations. Okay, and then we also specified these operations, right? And we had a lot of confusion about what pi 0 was what pi 1 was, right? Because 0 was using H0 and running things and running them backwards, pi 1. You can look at the definition from the previous lecture. Most likely you won't need it because we'll do the full proof today, hopefully. So it's not, it's just as an outline. Okay. And then the key point was that one can actually write, okay, so this was the part that where we stopped last time, which was that one can write the state sigma as follows. Okay, so it's phi p psi q, okay. And what are phi p and psi q? So these are, so phi p, so phi p eigenvectors of pi 0 plus pi 1, okay, pi 2, this is for b, and psi q, with eigenvalue, right. So, and they are the same thing, but for pi c0 plus pi c1 pi 2, okay. So of course you just have some eigenvectors, and because they're complete, whatever, complete on their respective spaces, therefore one can always expand some state in this basis. So I've not done anything very fancy. The reason why this is interesting is because they're able to prove, and this part is kind of where all the technical magic lies. So they're able to show that for all, so this is a claim, informal. There's a little spider web which says that for all poly epsilon, inverse poly epsilon, the following is true. So p such that p minus half is greater than epsilon and q minus half is greater than epsilon. So it's basically saying that you have an advantage, right? So that you're either outputting something, because it's a POVM, right? You can, if you write down the eigenvalues of the POVM, and then if you have a state and you look at the weight of your state on those different eigenvalues, then that will give you the probability of getting a certain outcome for that. So if this is your success probability, for example, then it will tell you with what probability you will succeed, and so on. Okay, so I'm not saying anything deep. I'm just saying that if you have a POVM pi, right, and you want to know what is the, and you can write it in some diagonal basis. So let's call it II, right? Then depending on the weight that you have on the ith basis, this will tell you with what probability you will get that outcome, right? That's all I'm saying. So here they're saying that you're going to sum over p and q, and the p and q are biased away from half by some epsilon, right? So you're getting some advantage, okay. And then so you look at, so all of these PQ like here, right? So you look at all the lambdas greater than some value. So similarly, you look at all the PQs with a certain value, and you look at the weight that your state is assigning to those, okay? And they're able to show that this is going to be approximately 0, okay? So this is kind of the magic, right? Because they're able to characterize the state sigma, and they're saying that the sum over all P's and Q's that are away from epsilon simultaneously, that weight is going to be small. That's all. Okay, and using this, then they can further write it as follows. So one can write that sigma is very close. So so therefore, sigma is very close to the summation of these states. So alpha pq, phi p, psi q, plus sum over alpha pq, phi p, psi q, okay. And what is the constraint? So p's are now, so this one is saying that p is not biased, so it doesn't have advantage beyond one, beyond epsilon, sorry, away from half, and this one does, okay. And then here it's flipped. So here p has an advantage and q does not. Okay, and this part they're calling sigma bad. Sigma bad for C, okay, because yeah, for B, okay, that makes more sense. Sorry, I miswrote. because for the so this is Bob and Charlie, right? So we're writing it in that order. So this is Bob's state, this is Charlie's state, and this one is saying Bob doesn't have an advantage, okay, and Charlie does. So this is bad for Bob. This one's bad for Alice. Oh, sorry, for Charlie. Okay. And so from this one can conclude that the winning probability is then, so the winning probability is at most half plus epsilon for any epsilon. Okay, because we wanted them to simultaneously succeed, right? And this one is saying at least one of them is going to fail, and you've characterized it. You've said that this is the only state that A could have set. Okay, and since this holds for all inverse poly, what does it tell you? It tells you that the success probability is negligible, right? That you could not have exceeded this. So this is the thing, but obviously the main thing is this characterization, right? So this is the magic. Why you can do this and why you can conclude that these amplitudes are small. Right, this is where the actual magic is. So the goal for today would be to get everything done except for these little characterization steps. So we'll do everything formally now, and try to get, and that lemma hopefully we'll do in the next class. So that's the goal. Okay. Yeah, give me a second. There's too many loose sheets of paper. I need to put them together. Okay, this is done. And now we're going to look at alrighty. So now we're going to start with coset states and basically just set up some notation and claim some properties. I'll write some of them for you as questions for the assignment. That we can't cover, but are still nice to check to get some handle. Okay, so this is section 4 from the paper. It's got more on coset states. Okay. So let's start with So here's the story. So we'll start with recalling some properties of coset states. Okay, and then we're going to look at the strengthened unclonable game in the quantum random oracle model, and then we look at the security of this game. Okay. So the security of this game is basically what we outlined, yeah.
Alpha PQ for all P and Q, which is like far from is approximately equal to 0. Do we say it's like statistically 0? Is it some negligible value which is close to 0?
Yeah. So this is negligible. There'll be some function of. So this would be like at most negl of lambda. With some security parameter, something like this. Yeah. Everything will depend on the security parameter, right? Otherwise, you can, otherwise clearly you can get. Yeah, maybe it's not so obvious, but at least for BB84 like states, you can always guess if there's only one bit, you can guess it with 3/4, right? So it has to be a bit more. Anything else? Is all good? Okay, nice. So now let's start with 4.1, which is just preliminaries for coset states. Okay, so now we're going to do coset states a little bit more formally. So we said this has to be a subspace, right? this is the parameters that you need to specify a coset state. A perp, remember, was defined as all vectors in F to n such that A dot B mod 2 is 0 for all A in the subspace A. Okay, so these are all the vectors that are orthogonal. Then there's a claim that the dimension of A plus the dimension of A perp is going to be n. Maybe I should have written a subspace. Yeah, okay, that's fine. Okay, and then notation. So we'll use this to say how many elements A has, that's the size of A, and that would be true to the dimension of A, right? So you can have or not have every vector, so there's nothing. So this denotes the size of A. Okay, and then finally, of course, we have the definition of the coset state that we wrote down last time. So let's quickly write it down again. Okay, yeah, so definition 4.1, coset states. So for any subspace A, F to n, and vectors SS prime in F to n, A SS prime, which is the coset state, is defined as 1 by root size of A, sum over A belongs to capital A, minus 1 S prime dot A acting on A plus S, right? So that was just the definition. So far we've not said anything new. Now here's a little bit of calculation you can do and check. So it holds that H tensor n acting on A SS prime. Any guesses what would happen? Okay, I mean you don't need to do the calculation, but it turns out that the state you get is A perp S prime S. Very cool. Okay, so it's very nice. You can try it yourself. Okay, now given A S S prime, okay, the coset state can be efficiently constructed. So this also I'll leave as an assignment. I looked up the original paper where they do it. It is relatively straightforward, but yeah, we'll not do it in class. Okay, this is the notation we are going to use. So A plus S is just going to mean V plus S, V belonging to A. So it's basically the set of all vectors in this thing. So it's pretty standard math notation. For perp, it's the same. Right, V belongs to A perp. That's fine. And then P A plus S and P A prime plus, A perp plus S prime was, membership oracles, right? So this we remember.
So what was the answer that how efficiently they were?
Yeah, I'm not going to discuss it in class. Like there's a
Answer. So
well, it's a statement. They can be efficiently constructed. I'm sorry, I think I'm not following what the question is. Answer to what?
can be efficiently constructed in poly lambda circuit size, for example.
Yeah. Efficiently would always mean poly-sized quantum circuit. Exactly. Yeah. So I'm being a little lax when I say efficiently. I'm just thinking of poly-size. I'm not worrying about depth, for example. That's what you were thinking about, weren't you? I knew it. Okay. Okay. Very nice. Okay, and now we're going to look at there's something called a canonical representation. So let's do that as well. It'll be helpful for later notation. So canonical representation of a coset is the following. So for a given subspace A, we define can sub A such that can sub A of S, say properly, can sub A of S is the lexicographically smallest vector contained in A plus S. Okay, so that's the. Okay, so A plus S is just this subspace, and then you look at the smallest lexicographically written. Like, so if if it's binary, like 0, 0, 1, for example, would be smaller than 0, 0, 1, 0, whatever. So you just find the dictionary order, you find the smallest. Okay, and this vector is called the canonical vector. Of the coset A plus S. Okay, good. So here's a quick note that you can check, that if S tilde belongs to A plus S, okay, then canonical AS is the same as canonical A S tilde. Because so if S tilde sits in S, there has to be some vector of A, right? That so some combination that's giving it. So you can use the same combination backwards to get the original S vector, and then you're essentially in the same space. Okay, so whatever answer. So basically, they will both give you the same A plus S, and then obviously the smallest element in two same identical sets is going to be the same. Okay, good. And then NB2 says what that. Okay, yeah. So this also will not prove. Actually, I don't know the full proof myself, but this one I looked up. This one I'm not so sure, but let's assume it for now, that there's a polytime computable. I think we gave a sketch last time actually, but so can A is polytime computable given the description of A. Okay, and A has to be polycized, I guess, as well. Otherwise, it will not be efficient. Okay. Okay, so given the fact that you can find this vector efficiently, therefore one can efficiently sample CS A, which is equal A S given S is in F2N. Okay, so I guess you can just sample an S uniformly and then run this algorithm. It will give you a uniform distribution. Most likely, okay, I haven't checked the details, but it looks that way.
So is it possible that you can create a superposition, but you are not able to compute one vector efficiently?
You're able to create a superposition over F2 and A?
So you are creating superposition of states that belong to A plus S actually, right?
Yeah, with the phase, yeah. The phase is the important part. Yeah, subspace, I think you can probably,
Yeah, so
depending on, yeah.
finding canonical vector is like knowing all these A plus S's, right?
Yeah. Because it's like sort of a representation. A plus S meaning for different S's. Like
No, different A's, because you are computing A plus S for different A's.
wait, so say your question again. What were you saying is
So
equivalent?
I'm thinking that capital A SS prime actually inherently requires knowledge of get a small A plus S for all small A's.
Yeah, but this statement is different, right? This statement is saying that you can find
And canonical AS is just like comparing all the elements small a plus s.
Yeah, so let's make a diagram. I think it'll help. So I think if I remember my group theory a little bit, it would likely partition the space, right? So you'll have A, this is, say A plus S0, A plus S1, whatever, and so on. So if I understood well, then canonical A sub S is just saying that, if I give you some S, so I give you some vector. Okay, so let's say this is some vector S. It will tell me which is the, in that coset, which is the representative smallest S, right? Representative meaning like the smallest one. And this CS sub A is just the collection of all of the vectors. So it'll be, so this would be in this notation. So C A of S, C S of A. In this notation would just be S0, 0, S1, and so on. While I thought what you were saying was you were spanning this space.
Yeah.
Because that's what used in the coset
so I'm still saying that because you can compute the superposition, so this means you know all these elements.
Yeah.
So canonical AS will also be efficiently computable.
Oh, you're giving an algorithm for computing canonical AS.
Yeah, I'm saying, is it trivial that do I need to prove that? Because
I think it depends on the size. I guess if A is no, but this can still be exponential sized. Yeah. Because you're adding.
that is why I was
No.
asking that if I can create superposition, does it mean that I know all of them?
Wait, give me a second though, because A we were anyway taking to be poly-sized, and if you're looking at, yeah, I think A is poly-sized, so you can actually just compute and check. I don't think there's too much trouble. A is exponential. Oh, the dimension is poly. Yeah. So then it's not so clear. You're right. Yeah. It's 2 to the.
Can't we use something like QFT using the basis vectors or something to compute ASS prime?
The question is not whether you can produce ASS prime efficiently. I mean that you can do.
No, so
But
I'm saying like we can produce ASS prime without knowing all ket A plus S.
yeah, I don't think you need to know all AS. But Uttam was saying that somehow you may be able to, given ASS prime, you might be able to extract A plus S. And so I'm not so sure if that's entirely true. Yeah.
Bitwise, and since A is a subspace.
Can you do it bitwise since A is a subspace? Can you do what, like to extract, like to list all elements in A SS prime? Yeah, let's not get stuck on these details. They're nice and they feel concrete, but yeah, we'll do them in the assignments. For now, let's continue. There's a lot to do, you guys. We are already on I don't know which lecture on this uncloneable encryption stuff. Okay. So the point was that, yeah, so one can efficiently sample, right? So this part is okay. And then here's an imported lemma from a previous paper. Okay, so this is lemma C.2, I think, from this CCL Z21. You can look it up. What does it say? It says that.
Sorry, just a clarification. So this set CSA had like it's exponential size set, right? CSA.
This will probably be just the
Because
sort of quotient, right?
right?
Yeah, so it should be the quotient. So if A is dimension.
No, I'm just looking at this set definition from here because S belongs to F2N, and for each S there is a canonical.
No, but many of them will give you the same answer, right?
Oh, many of
No, but even then it will be exponential, right?
Yeah, it depends on the size of A, right? So if A, for example, is like the entire set, then you will have only one vector. I mean, the answer to your question would depend on what is the size of A, because you're making cosets, right? So you're partitioning the space. If you take one giant A, then you have only one representative element. Like the, so I was drawing this, right? So depending on the size of A, it's basically the number of partitions. This is just basically picking representative elements for each of the partition. Okay. Okay, so for a fixed subspace A, the coset states S in CS A and S prime in CS A prime A perp form an orthonormal basis. Okay, that's good. And now comes the main. So one of the two main theorems from previous works that is going to be relevant here. So here's the main theorem. Okay, so theorem 4.3. This sort of story, one of the main results, main relevant results. Okay, from the previous paper, from previous works. Okay, so what does the theorem say? The theorem says the following. So it says you let A be a subspace, be uniformly random of dimension lambda by 2, okay, and you take SS prime to be two uniformly random vectors F2 lambda, okay. You let epsilon greater than 0 such that 1 by epsilon is little over 2 to the n by 2. Okay.
So how many coset states are there? Like they form orthonormal basis, and you took S and S prime from CS.
Yeah, no, we had that theorem, no, that the dimension of S and dimension of S prime add to n, so then they'll span. It should be okay, I think.
So they are spanning 2 to the n dimensional space?
Yeah, they have to, right? Because it's they're spanning F to n, yeah. So dimension of.
They don't depend on A?
No, you're taking the dual subspace as well, right? So if you take a very small A, the A perp will be very big. So you will be able to span them. Yeah. Right, like for example, if you take A perp to be, say, the 0 subspace, right? So you basically every single element becomes.
Yes.
So yeah, if you take A to be like the whole thing, then A perp would likely be everything else, and then yeah, should be able to do it. I haven't checked this, the completeness. I checked the orthonormality. I didn't check the completeness, but I'm guessing it's okay.
So orthonormality is straightforward because of the A perp.
Yeah, from the definition you should get it. Yeah. Okay, and then given one copy of ASS prime, and so far what we've done is, so this is just to set up the coset state. Epsilon is just saying that 1 by epsilon is, exponentially bounded. Then the oracle access. So you're given one copy of this state, okay, and you're given oracle access to P, the membership oracles, right? So P A perp plus S prime. So if you're given this, then an adversary needs omega root epsilon 2 to the lambda by 2 queries to output a pair VW satisfying V belongs to A plus S and W belongs to A perp plus S prime with probability at least epsilon. Okay. So is the statement clear? So the statement is saying you're given access to this coset state, okay, where A is chosen uniformly to be of dimension lambda by 2, but otherwise random. S and S prime are random. You're given psi epsilon, and now you're also given. So you're given the coset state that has been sampled like this, and you're given access to membership checking oracles. Okay. Even then, if you make only these many queries, okay, the probability that you can output a VW from the corresponding subspaces is at most epsilon. Okay. And the way we are going to use it is we're going to take we only care about negligible and exponentials, so negligible and non-negligibles, and so therefore we'll rewrite it. Okay, so the corollary is so there exists an exponential function x0 such that for any query bounded so polymany queries to membership oracles P A plus S and P A perp plus S prime. The probability that algorithm A outputs I didn't complete this. A query bounded algorithm A is such that probability that A outputs a pair V comma W such that V is in A plus S and W is in A plus S prime is at most 1 by exponential 0 of lambda. Okay. So this basically just follows immediately, like you have to put polys and and then that should sort of pop out. Okay, so what this result is basically, where we are going to use it is, we had this tripartite thing, right? This triple for the adversary, it had this sort of a form, right? And A would typically get access to the coset state. We're going to sort of argue that if you're using a random oracle and you reprogram the random oracle at SS prime, then using this fact, we'll prove that the adversary A cannot make the distinction. So nothing will change.
Can you repeat that once again?
So the idea is that A is going to get access to ASS prime the way we're going to use it, and we will argue that using this statement that and it'll also have access to a random oracle. Okay. So what we're going to argue is that if in the random oracle we change the value of the random oracle at SS prime, then A cannot distinguish between that case and the original random oracle. Because if it could, then you violate this statement. Okay, so this is what we'll prove. So that's why this is useful. And the next thing we're going to do is okay, so I'll need more space. Let's make some more space. So the next thing we're going to do is we're going to have like a search version of the monogamy of entanglement game, where we're going to have to output the full information and not just distinguish. Okay, so but obviously we'll need to use distinguishing games for the actual security, so that's where the strengthening comes in. So this is the monogamy of entanglement with membership checking oracles. Okay. So definition 4.5 Okay, so we're going to let lambda be a natural number, okay, and consider the following game. Okay, so here's a challenger. Okay, the challenger uniformly samples. At this point, whenever there's A and we're talking about sampling, it's always going to be this. You do it from f lambda uniformly and of dimension lambda by 2. Okay, and you sample SS prime vectors uniformly. From. Oh yeah. Okay. Now I have to be more careful. Because we set up the notation. So this is the set of canonical strings from A cross canonical strings from A perp. Okay, and we already claimed that you can efficiently sample, so everything so far is efficient. Okay, so this is what the challenger does. Okay, and then the challenger is going to send A SS prime. This is what the adversary. And this is access to membership checking oracles, so P A plus S and P A perp plus S prime. Okay, so A has access to this membership checking oracles and gets the coset state as input, and produces a bipartite state, sends it to Bob and Charlie. Okay, it is very similar to what we saw earlier. Okay, so you get a description of A, right? Same here, description of A, the subspace. And they continue to get oracle access to, I'll just say membership checking oracles. Okay, MCO is membership checking oracles. I'm just being slightly lazy. And this is what I'm calling MCO, membership checking oracles. Okay, and now they have to output S sub B prime, and similarly here S sub C prime. Okay. And the challenger is going to output accept if SB matches SC and they are the same as S. And similarly, SB prime has to be the same as SC prime, has to be the same as S prime. And if anything goes wrong, the challenger is going to reject it. Okay, and then the output out. Okay, so that's the game, and obviously it's very interesting to actually analyze the game, but we'll not be able to do it because even without doing the proof there's a lot more to be done. So what we are going to do is we're going to show somehow that here you see you're outputting the entire string, right? So this is similar to when we were doing BB84 and we were asking for the entire X to be output when I gave you the input as the BB84 state. Right, and we argued that that's not enough for security, right, because you might still leak some bits. So similarly, this will not be enough for security, but they are going to show that, they're going to modify it in some way by using random oracles and so on, and they're going to show that distinguishability would imply that you can actually find them, and then finding the strings is impossible, and so that's how we are going to do the proof. So we're going to assume this and show that distinguishability would imply that you can actually find them, and then that would be impossible. So that's why we're doing this. But let's see what was actually proved.
But this is peculiar in their case, right? Because distinguishability in general will not imply that.
Yeah, that's why they had to use coset states, and they're using properties of coset states and so on. It doesn't happen in general. You're right. So the main reason they have to, so what property, right? You can ask, okay, what property of the coset state? And the property is precisely this, that even given access to these membership checking oracles, it's hard to find these strings. For BB84, that's not the case, right? Because we saw that theorem, right? That said that if you give membership checking oracle, like so if I give you the BB84 state H theta X, and I give you a membership checking oracle, if I give these to you separately, you cannot find X entirely. But if I give them to you together, there's a theorem that says that you can actually find X. Making polyqueries, of course, yeah. Here, that's not the case. Even if I give you the membership checking oracle, you're not able to do this. And why they care about the membership checking oracle is because it allows them to reprogram the random oracle at X prime, which you could not do. So that analysis doesn't go through. So you could potentially use any other class of states as well, which has this property even against given access to membership checking oracles. Okay, so what is the statement? Okay, so I forgot to write. So we denote the advantage or the success probability of the game by, might as well, okay, advantage A, B, C for a given lambda. Okay, and the theorem, as I already said, basically says that this is inverse exponential. So there exists an exponential function exp. Okay, yeah, sorry, this is supposed to be a different typeface, but my handwriting is the same. Such that for every lambda in n plus, and for any query bounded, that is, you do poly many queries, p sub a plus s and p a pub plus s prime. So such an adversary, so we write it as a triple. It holds that ABC is going to be at most 1 by exponential. Okay, so that's the statement. It would be very nice to actually do the proof. I don't know the proof, but I doubt we'll have the time. Okay, nonetheless, let's see how this is strengthened. Okay, so there are some remarks about how this was used and how this was strengthened and so on, which I'm going to skip. You can look at it in the paper. Let's move on to the strengthened monogamy of entanglement game, right? That's the one that we care about. In the quantum random oracle model. Okay. Yeah, it's actually nice. We can write it here, right next to it. All right. So, what's the construction? Oh, sorry. What's the definition? So here's the definition. Again, lambda is n plus, and H is a random oracle, which goes from f2 lambda cross f2 lambda to 0, 1, n lambda. Okay, and n is like somehow omega lambda. This part they don't explain all that well, but it looks like you need to have the random oracle have like a big output. This is the be a random oracle. Right. Okay. So what is the game? The game is the following. Okay. So the game is a little bit slightly peculiar, but mostly makes sense. Okay. And okay. So we assume that. So okay. So then consider the game. Okay. So consider the following. Say the following. And assume, so I'm now going to write it explicitly now that A, B, and C have access to the membership checking oracles. So P A plus S, P A pub S primes. Okay, and what is the game? The game is the following. So here's the challenger. I'll just write samples A, okay? So we know what it means, because we've done it many times. Lambda dimension A is lambda by 2. Okay. It samples SS prime. Let me write it better actually. Okay, samples SS prime uniformly from, it's the same as before. What was this? Canonical string, right, of A and A prime. And the bit B, okay, these are uniformly sampled, and computes the following. So it computes W, which is H, the random oracle evaluated on SS prime, XORed with B dot delta. Now what is delta? I didn't tell you what delta is. So delta is what A sends. Okay, so A in the beginning is going to send a string delta of length n. Okay, n is the same that we had before. So note that the output of the random oracle and the string length of delta is the same. Okay, and then the challenger will send the coset state and the bit W. Okay, so they'll send A SS prime and they will send this W. Okay, good. And you're going to get B and C. So this is Bob, this is Charlie as before, and they get description of A as well. Description of A. Okay, and again they have to output B sub B and B sub C. And the criteria for winning is, okay, what should be the criteria for winning?
Output be equal to B.
Exactly. So B sub little b should be the same as B sub little c should be equal to B, because basically they're trying to see if this adversary can distinguish between a random W and a W in which you actually XOR the message. Okay, because if they can't, then they can't really, they don't know what message was sent.
But B is a bit, what is B dot delta?
Yeah, so this is either you XOR with delta or you don't. It's just saying, so
No, the side is not same, right? B and delta.
it's a scalar. It's a scalar multiplication. I mean, you can think of it as a scalar multiplication. It's just
when
saying.
B equal to 1 is just delta, when B equal to 0 is nothing.
Exactly. Okay. And otherwise you reject. Uttam Bhai's compiler was failing. It's like type mismatch. That's good. Very good. Okay, so that's the output. Okay, and our so most of our work would be in showing that this statement is true. That you can't win this game with probability more than half. Okay, so that's going to be the heavy lifting. But before we do that, so I'm going to write down the theorem now. And then before we do this, after I write down the theorem statement, before we do the proof, I will show you how this actually gives us the security for the construction that we initially started with. Right? So we will show how this implies unclonable encryption. And then we'll prove this using some other statements that we'll assume, and then we'll do one more step and then we'll stop. Yeah, these things are involved. I'm sorry. I thought it would be simpler, but it's very clever and very involved. So here's the theorem, 4.8. What does the theorem say? The theorem says that let n equals at least omega. Okay. Then for every lambda in plus and all query bounded algorithms ABC, the advantage ABC in that game. Okay, oh yeah, sorry, I forgot to say, and denote, let advantage ABC denote denote success probability above. Success meaning accept probability, right? Okay, good. So the advantage for a lambda is at most half plus negligible. Okay. So, ooh, nice. We have half an hour, right? It's 11, so we'll sit until 11:30. Good. Okay, so this is the main theorem that we're going to focus on. So we defer the proof for a minute. So defer the proof to next class. Okay, but now we're going to look at. Actually, maybe in the next section, maybe is better. Okay, and yeah, let's finally see how to use this to build unclonable encryption. It might be trivial for some of you, but let's do it anyway. Okay. So here's the scheme. So Gen is okay, so Gen does the following. Okay, it returns sk as A, okay, where A is sampled, f2 lambda dimension A lambda by 2. Okay. So the secret key is just the subspace. Okay. Encryption, given access to the random oracle. Okay, this is precisely what we were discussing at the very beginning, right? That you sample SS prime, right? Like we were sampling X and theta was the secret key, so now you're sampling SS prime from CSA cross CSA perp. Okay, and then you return A sub SS prime. Okay, and then we decrypt SK equals A SS prime C. Okay, so decryption is sort of straightforward because from ASS prime, actually, maybe it's actually not. Okay, so we don't need this one. Let me keep the other game. So decryption is straightforward if we can assume that, if you assume that given the description of A and the coset state, if you assume that you can extract SS prime, right, then we're in good shape. Where's the message? Okay, wait, I don't think I wrote the complete encryption. Sorry, I messed up. I forgot to write the XOR. Yeah, M. Yeah, it's likely you're also sending M XORed with H of SS prime. But let me check just to be absolutely sure that I didn't mess up anything. Yeah, okay, so this part is C. It's defined to be C. Okay, so you output this state and the message. Sorry, I forgot to encrypt the message. I just sent the unclonable state. Okay, good. So how does decrypt work? Yeah, that's what I was trying to write here. So the decrypt algorithm does the following. Okay. Okay, so we are going to use the algorithm that we mentioned earlier, that given a vector tells you the representative vector for that coset that it belongs to. Okay, so you proceed as follows. Okay, so we have a ss prime is the same as 1 by root a sum over a minus 1 a dot s prime a plus s, right? So that's the coset state. I've not done anything, we've just written coset state. Okay, now we're going to use the algorithm that outputs, so this was, what was it called? Was it called canonical? I think we wrote can sub a, right? So using can sub a, right, you produce the following state. So you transform it into, so you apply to this vector, okay, and because we chose S to be coming from canonical strings, the canonical string for this vector will be what?
Just S.
Right. So it would just be S. Right? Just by definition of the canonical string and the fact that we're using S to be a canonical string to begin with. Okay, so it's going to output S for every element A plus S. Okay, so it's essentially just, you get the coset state back except that you've extracted S. Good. So this is the same as SS prime, you've extracted S. And now, so this is similar to, I guess, your intuition about using Fourier transform. So since we are in Fn2, the Fourier transform is just H tensor n. And we're going to recall that H tensor n acting on ASS prime. What was this? Exactly, A perp SS, right? This is what the definition was. Okay, so what does that give us? So this will give us A perp S prime S, which is the same as you sum over A in A perp now, right? You have A dot S, and now you have A plus S prime. Okay, and that's what we wanted, right? We wanted S prime to come somehow outside. And now we can run the same algorithm. So you can use canonical. Yeah. So that's why I'm saying you just. You can add it. Maybe that's better. Yeah. Okay, and then you can run this canonical algorithm on the perp, and then you would have A plus S prime S with S prime, right? So you extracted both S prime and S. Okay, so using this. Can you speak up? I'm a little bit deaf.
S might not be the lexicographically smallest string.
What is the definition of S? Look.
Oh, okay.
Yeah. They took it into account from the definition. But you're right. In general, it may not be. But here, by definition, it is. Yeah. Okay. All good. Okay. Great. So you get this, and once you have done this, right? So decryption. You're given C. You run this procedure that I described over there to extract SS prime, and then you output C XORed with right to remove this so that you can get M back. Correct? Okay. So far that was the scheme. Doesn't say anything about the security. So let's do that.
Given that we can compute can sub a polytime, and so we can compute CS sum. So isn't it?
We can compute. We can compute what?
CS.
What is CS?
The CSA, CSA.
Ah, yeah, these, yeah.
Yeah.
Uh-huh.
Isn't it possible for the adversary to do the same procedure?
Who's the adversary?
The
There's A, B, C. You mean A itself?
yeah.
Yeah. So here you're crucially using the fact that.
A is a secret.
You're using the fact that the description of A is given only to B and C. Yeah.
Oh.
The description of A is not given earlier, right, in the game. Yeah, which is the same as that it's a secret key. Yeah. It appears here, right, in the game. Okay. Anything else?
So how are you using this
Canonical A to get.
This is step. Like first to second is step one.
Oh, you just run canonical A on A plus S, right? It will give you S.
What does it mean run canonical?
It's a classical algorithm that I asserted can be done efficiently, run efficiently. That's what we discussed earlier, no? It was a claim. It was just a claim. I didn't prove it.
No, that is okay, but this, so
I can run it coherently. If I have a classical algorithm that produces some output, I can run it on a superposition, right? Nothing stops me from running it on a superposition. You can. Yeah, you can run it unitarily, right? Like it should be fine. So the way to think about it is that even if it's not like suppose that it's irreversible and you need some auxiliary qubits, you can run the algorithm. You get your answer, you copy your answer, and then you run the inverse of the algorithm. So you get everything back in the state that it was to begin with. Yeah. Okay. So there shouldn't be any problem. Okay, very nice. So now we're going to try to see why this scheme is secure. So let's do that. Okay, so the proof. Yeah, actually, the way I was describing it earlier was a little bit incorrect, because this is the game that we intend to use, but the security game is a little bit different, right? Because the security game, I should have drawn the security game. So the security game was that the challenger sends two messages. Maybe I can draw it with. The security game would be that A sends two messages M0, M1, right? And the adversary sends the encryption. So in this case, they would send ASS prime, and they would take M sub B, XOR it with HSS prime, right? And send it, and then the adversaries. Sorry, my adversaries are a little bit stretchy. So you have B and C, right? And then they get the description of, they get the secret key, right? So the secret key was A, so they get the secret key, which was A here. And they all have access to the oracles, and they have to output which message was, among M0 and M1, which message was encrypted, right? So that's the game that we want to show you can break. That you cannot break, and the way we'll do it is we'll consider an adversary that breaks this game, okay, and we'll use that to break this game. And because we already stated the theorem that this cannot be broken, the scheme would be secure. Okay, is the strategy okay? Well, how do we do this? And this challenger we're going to call the challenger for monogamy of entanglement. Oh no, sorry. The challenger for monogamy, this is the one we're going to call challenger for monogamy of entanglement. Okay, so how does it work? Okay, so suppose that ABC breaks unclonable indistinguishability. I don't know why they use CP actually. That I don't know where this fact is used. Unclonable indistinguishability. Okay. So yeah, maybe I'm missing some subtlety, but we'll see. So we show how to construct A prime, B prime, C prime, right? That breaks this game. So let's call definition game in definition 4.7. Okay, good. Yeah, so A here. So A is the original one, right? So it's the one that was breaking in CPA. It's going to send some message M0, M1, right, as it was. So now what A prime is going to do is, A prime is going to define delta to be the XOR of M0 and M1. Okay, and it will forward this. Okay, I think I messed up in my notes, but you just forward delta, okay, to the Monogamy of Entanglement game. Okay, so all I did was I got the messages M0, M1 from the initial adversary. I computed a delta, which is just the XOR. Okay, and now the adversary is going to do the following: to send me SS prime and W. Okay, and what I will do is I'll take the W that I got from the challenger. Okay, and I'm going to XOR it with M0. Okay. So far, this challenger would have either sent, would have either sent delta XORed with the random oracle, okay, or sent just the random oracle. Okay. So if it sent just the random oracle, okay, C would become the random oracle XORed with M0, okay. And if they had sent the random oracle XORed with delta, then C would become the random oracle XORed with M1. Is that clear? Yeah? So when B is 0, C equals M0 HSS prime, right? And when B is 1, becomes HSS prime XORed with M1. Okay? So far so good, very nice. Okay, and so now you send this to the adversary for the initial game, the one that breaks the unclonable indistinguishability. And now you see the distribution of the ciphertext is exactly as it was supposed to be in the unclonable indistinguishability game, right? You're either given an encryption of M0 using the scheme, right? The scheme says this is how you encrypt M0, or you encrypt M1, right? So you've gotten exactly the same distribution, and for exactly the same Bs. So when it's 0, it's encrypting 0, and it's 1, it's encrypting 1. So now you basically just forward whatever was forwarded. So you run B prime and C prime. Okay. So B prime and C prime basically just run B and C of the original thing. Okay, and then they use it to get the outcome, and yeah, that's it. That will break the game. Okay. Ooh, we have more time. Very nice. Okay, good. So now let's try to make some progress with the actual proof. Okay, so now we're going to try to prove this, or rather this, 4.8.
So what you just showed that if I can break this scheme,
Yeah.
like the scheme that you removed, then I can break this one as well.
Yeah, and now we'll prove that that cannot be broken. Yeah.
And that you claimed, right? That you claimed informally before.
No, I claimed it formally here. Isn't it? Am I saying something wrong? It's just this game, yeah. It's that one. It's saying that game you can't succeed with half plus neglect.
You just showed that it will imply unclonable.
Yeah. So this is so far I've only shown that if you have this game, it is enough to construct unclonable encryption, and now we'll try to understand how to prove the security of this game. And we will unfortunately still have to miss out on the really nice parts, but we'll make some progress on how the proof goes. Okay, so now this is the section that I said I'll defer. Okay, so proof of theorem 4.8. Yeah, now we're going to have to consider hybrids. And there are, okay, so there are 3 hybrids. So hybrid 0 is, the original game. So hybrid 0 is this thing. This is the original. Okay. Hybrid 1 will do the following. So it's the same as hybrid 0, except A is reprogrammed as follows. Reprogrammed as follows. Yeah, SK should actually just be a description of, because otherwise A is exponential, right? The size. Sorry about that. Okay, so how is it reprogrammed? So it's reprogrammed as follows. So this is the same as the original one, except that you've replaced the evaluation at z equal s and z equals s prime with another random value, which is independent of everything else in the random oracle. Okay, where q in 0, 1, m is uniform. Let's just do this sample uniformly. Okay, so that's hybrid 1. So that doesn't look very hard. Hybrid 2 is going to be a bit more involved. So let's draw it. Oh, there are some prerequisites that I forgot to introduce about Jordan's lemma and things like that. Maybe I should have done that. Okay, so let me write the. You know what? We have about 7 minutes. What I'll do is, so hybrid 2 we'll write next time, okay? Because if I erase it, then I'll have to draw it again next time. it's a bit tedious. So hybrid 2 we'll do next time. Okay. But in the meantime, I will tell you some facts that we are going to use in the proof. There are actually quite a few, but we'll do it step by step. So I'll give you the prerequisite stuff. So I'll give you the prerequisites for the first part, and this is going to be some statements about Jordan's lemma. Okay. Okay. So, yeah, I'm sorry, I'm not giving you all the prerequisites at once because otherwise it gets a bit tedious. Yeah, tedious has become my new favorite word apparently. 2.3 is more on Jordan's lemma. Okay, so so they've adapted it from Regev's paper and some notes from Thomas. What does it say? It says the following. So you have lemma 2.2. So let W be a number between 0 and 1. Okay. H be a finite dimensional Hilbert space. Which is usually all that we consider in these kinds of constructions, and pi 0, pi 1 be any two projectors, because it's a very general statement. Projectors in H. Okay. Then number 1, there exists an orthogonal decomposition of H into two-dimensional subspaces. So H can be written as a direct sum of these two subspaces that are invariant under pi 0 and pi 1. Okay, so the first statement is that you can split your Hilbert space into these direct sums, right, such that when you act on them with pi 0, pi 1, the subspaces don't talk to each other. They just, all the vectors in the subspaces remain in their respective subspaces. Yeah? Okay, so that's one. The second says the following.
Assume something about dimension of H, isn't it?
Finite.
No, but direct sum is even dimensional. Right? The direct sum that you are writing is even dimensional.
It could be like S, it wouldn't it depend on the dimension of SI?
But you said two dimensional.
Oh yeah, okay, why did I do that? It could either be 2 or 1. Yeah, I don't, yeah, you're right. That's a bit weird. Okay, we'll see, but yeah, ignore Uttam, okay, he knows too much. So SI is spanned by, no, we will see what's going on in a minute. No, okay, so SI is spanned by 1 or, maybe it's at most, maybe that's probably what, maybe I skipped a second, or 2 eigenvectors of omega pi 0 plus 1 minus omega pi 1. Okay. So SI is spanned by, 1 or 2 eigenvectors of this thing, is exactly what the statement says. And then the third, let me write the third here. Whenever SI is two-dimensional, there exists a basis for it in which pi 0 and pi 1 restricted to that subspace take the form pi 0 SI is just this vector, okay, and pi 1 SI is CI square CISI CISI SI square. So C is cosine and S is sine. Okay, yeah. So that's the statement of the lemma. That's not actually what we use in the proof. So what we use is a little bit is the following statements. Okay, so we're going to use the following. Okay, so yeah, so the proof of this we may or may not do. I don't know. We'll see later. It's kind of nice. We might do it when we do verification, okay, the proof of this statement. But for now, you just need to understand the statement. The statement is just saying that, if you have any such projectors, you can always decompose your Hilbert space into, these giant little diagonal blocks, and the vectors in each block under the action of pi will not talk to anything else, they'll stay inside the same block. And you can show that if you restrict to any of the SI blocks, then there's a very clean characterization of these projectors. Okay, so one of them you can always write as 1, 0, 0, the other one you can write as just the outer product of two vectors. Okay, so that's the statement. Okay, now so for any two, oh shoot, it's time. Damn it. Okay. Okay, yeah, let me write it next time then. So next time I'll write the statement that we'll actually use, and then we'll continue with the proof. Okay. Right. Thank you. Feedback.